Welcome to The Explainer. Today we're looking at something absolutely mind-blowing. We are exploring one of the most fascinating phenomena in physics, one that is, quite literally, powering our modern world right under our noses. The mechanics and applications of total internal reflection. Okay, yeah, I know, it sounds like a heavy physics textbook term, right? But honestly, it's essentially just the science of building invisible pipes for light. By the end of this explainer, you're going to see exactly how this single scientific concept acts as the silent hero behind your everyday life. We're going to break down exactly how we manipulate light to do all our heavy lifting. Okay, let's dive into this. Think about it for a second. When you stream a 4K movie, or, make a completely lag-free video call across the ocean, or download massive files in just seconds, how does that data actually travel so incredibly fast across the globe? It feels like magic, right? Or maybe you think it's satellites. Well, actually, it's a highly engineered manipulation of light. Deep under our oceans, there are massive networks of physical cables that basically act like high-speed garden hoses, but instead of water, they are pumping light all across the globe. We're utilizing this hidden phenomenon of guided light to instantly transmit information. And to understand how we actually manage to pump that much data that far without it just leaking out into the Atlantic Ocean, we really need to look at what's physically carrying those signals.
Section 1. The secret is in the fiber, trapping light for global communication.
So, to understand how we trap light inside a fiber, we really have to understand what light naturally wants to do first, and this brings us to a foundational concept, refraction. Refraction is basically the optical phenomenon where a ray of light bends as it passes from one medium into another. But why does it bend? Well, it all comes down to density and the speed of light. Light actually travels at different speeds depending on the material it's moving through, what physicists call a material's refractive index. For our purposes today, we're looking at what happens when light travels from a denser medium, like glass, into a rarer or less dense medium, like air. Normally, when light makes this jump and speeds up, it bends away from what we call the normal line. It doesn't just stay put. Its path gets completely altered as it escapes into a new environment. Imagine a leaky garden hose, right? When the water inside hits a hole, some of it just spills right out into the surrounding yard. And that's essentially what normal light is doing here. It's leaking. Now, this beautifully illustrates the absolute critical difference between what normally happens and the phenomenon we actually need to achieve. In a standard refraction scenario, the light ray hits the boundary, bends, and just completely escapes into the rare medium. The energy bleeds out. It's exactly like a punctured water pipe losing water pressure. And obviously, you wouldn't want your high-speed internet leaking out halfway across the ocean. But under the perfect conditions, the light doesn't escape at all. Instead, it reflects completely back into the denser medium. The pipe is perfectly sealed. The light gets trapped, just bouncing off the inner walls without losing a single drop of data. This complete reflection back into the same medium is the whole ballgame for modern optics. It's exactly how we keep the signal strong all the way from New York to London. So how do we actually force light to do this? That brings us to Section 2, hitting the critical angle, the journey of a light ray.
We can actually walk step by step through the exact mechanics of a light ray's journey to see how we get it to stop refracting and, start reflecting. Think about turning the nozzle on a hose and changing the exact angle at which you shoot the water against the inside wall of a pipe. In step 1, we gradually increase the angle of incidence. That's just the angle at which our incoming light hits the boundary between the two materials. As we increase that input angle, step 2 happens. The angle of refraction also increases. The escaping light bends further and further away from its original path, getting closer and closer to just skimming the surface. And then, eventually, we hit step 3. At a very, very particular angle of incidence, the refracted ray bends so dramatically that it travels exactly along the boundary line separating the two media. It's literally skimming right along the edge. This highly specific, magical tipping point, that is known as the critical angle.
So, the absolutely crucial point is what happens next. When the angle of incidence becomes greater than that critical angle we just established, the light can no longer refract into the rare medium at all. Physics literally won't allow it to escape. When your angle of incidence pushes past that tipping point, the mathematical result is absolute, total internal reflection. The light perfectly bounces back into the denser medium. We've effectively trapped the light ray, creating this continuous, unbroken bounce that allows the signal to travel indefinitely through the core of the pipe.
Which leads perfectly into Section 3, the two golden rules, strict conditions for total internal reflection.
Now, nature doesn't just hand us this phenomenon for free. For total internal reflection to actually occur, two absolutely strict, non-negotiable conditions must be satisfied. First, as we covered, the light absolutely must be traveling from a denser medium toward a rarer medium. Think back to our light pipe analogy. If you're building a fiber optic cable, the inner core has to be optically denser than the outer layer, which is known as the cladding. If you get that backwards, well, the water leaks. The light just escapes right out the sides. Second rule, the angle of incidence must be greater than the critical angle. If you fail to meet either of these two golden rules, you don't get that perfect bounce. Instead, normal refraction takes place, your signal degrades immediately, and the light simply escapes into the void. These two rules really are the absolute bedrock of optical engineering. Now that we've mastered the microscopic physics, let's zoom out to Section 4, Real-World Applications, from medicine to telecommunications.
Now, what's really interesting about this is that because we can guide light so efficiently, treating it exactly like water flowing through a perfectly sealed, endlessly bending hose, we can revolutionize vastly different fields. In global communication, optical fibers rely entirely on a dense glass core wrapped in a rare glass cladding just to trap lasers. Inside these cables, light signals continuously undergo total internal reflection, just ricocheting down the line. This is exactly why our internet data can travel over incredibly long distances, underneath whole oceans and across continents with virtually zero loss of energy, and at speeds that honestly boggle the mind. But the applications don't stop at telecommunications. No way. In the medical field, this is the exact same principle used in endoscopy. Doctors use bundles of flexible optical fibers to safely navigate light through the winding, intricate pipes of the human body. It allows them to illuminate and observe internal organs without ever needing invasive surgery. And even in everyday optical instruments, it perfectly bounces light inside the prisms of your binoculars to fold the light path, giving you a crystal clear, magnified, correctly oriented image in a super compact device. All of these marvels of modern engineering rely entirely on consistently hitting that one critical angle.
It really makes you step back and wonder, doesn't it? How much of our modern world, from the high-speed global data networks keeping us all connected to the life-saving medical devices navigating the human body, relies purely on our ability to perfectly trap and pump a beam of light through a glass pipe. It's a pretty brilliant reminder that the most profound technological leaps often come from deeply understanding and then perfectly controlling the fundamental rules of nature. So what else could we completely transform by just tweaking the rules of physics? Thanks for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.